started. All right. So today we're gonna continue our discussion of path integrals, but the past two lectures was about formulating quantum mechanics using path integrals. Now we're gonna use path integrals in quantum field theory. So I will start by a summary of what we went over the last lecture. So we developed a perturbation theory for small interactions in quantum mechanics. So you had some sort of interaction, it's quantum mechanics, that has a free part, for example, that's Gaussian, and then there is an interaction term, GV. I didn't put G in there, but you could imagine there's a coupling sitting in front of your interaction term that we're going to take to be small. The perturbation theory that we set up was in this regime. So this is every time you're talking about perturbation theory, you have to make sure you have a small dimensionless parameter, and you have to keep track of it. This is the small dimensionless parameter. Now, this small dimensionless parameter this condition is a little bit too strong. Now, I invite you guys to think about when is this a good approximation or not. But this is literally the approximation we're working with. I already put a space in there. Anyway, so then we said that we had the propagator in quantum mechanics. In the perturbation theory, we could expand it as a free propagator plus a first order interaction term. We performed the path integral for the propagator. We derived the path integral expression for the propagator previously. And here I'm assuming that the interaction term is only a function of space as independent of momenta. Therefore, all the path integrals that I'm doing are path integrals only in real space. I've already performed the Gaussian path integral and the momenta. Originally, the full form of the propagator is a path integral over the phase space. Okay, now we did the path integral for the free propagator. We found this expression. I want to go through it and explain a few aspects of this. There is the step function that you find, which enforces final time being larger than initial time. We call this the retarded propagator. We gave this a name. This is a factor that basically what matters here is that it's 1 over delta t to a power of d over 2. Then there is this Gaussian phase, right? So this is the full structure of the propagator. Now, to make this a little bit more intuitive, you would go to Fourier space. The Fourier variables are going to be spatial momenta and energy. That's Fourier variable conjugate of time. And in the Fourier space, you're going to get the following expression: 2 pi h bar to the power of d. There is the momentum conservation that comes out. There is the energy conservation that comes out. So these are term by term, we could interpret it. Then there is this term, which is the core of the free propagator. There is a bit, so it's 1 over dispersion relation. And we said that we often shift this by some I epsilon. We call this I epsilon prescription, similar to Feynman propagator. Because in the Fourier transform, otherwise we're integrating going through a pole. So we just analytically continued this, and then this I epsilon is related to this retardedness, right? Then we commented on the fact that this dispersion relation has only one pole as we integrate. That has to do with the fact that we're in non-relativistic theories. Whereas in the relativistic theory, in comparison, we saw that there were 2 poles. One of them was a particle, the other one was antiparticle. As we're integrating through, we had to make sure, so we found three different propagators, right? There was a retarded, there was an advanced, and there was a Feynman propagator. The Feynman propagator went under the antiparticle pole and over the particle pole. Then to get some intuition as where this expression comes from, it's actually pretty simple if you think about it in terms of Green functions. So this is a Green's function for Schrödinger operator. That means that it solves the following differential equation, right? From translation invariance, you know that this function is only function of delta x's and delta t's. Translation invariance and time translation invariance is precisely the origin of the momentum conservation and energy conservation. right? Just this is the connection between symmetries and charges, conserved charges, right? That we saw in Noether's current, Noether's first theorem. Then you look at the free propagator, you Fourier transform the Schrodinger operator, it becomes E minus K squared over 2M. That's just a dispersion. So you have E minus K squared over 2M is equal to 1 because the Fourier transform of this guy is just 1, right? Now, how do you solve this equation? Well, you just divide 1 by this dispersion. And this I epsilon is just to make sure that you're picking up the retarded propagator, right? So this is the origin of it. There's nothing mysterious about it. So if I come to you and now here's the thing. I come to you and say, I have a theory. And here's the green 2-point function of it, green function. Here's the 2-point function for it, right? If you want to know the particle content of that theory, what you would do is you would Fourier transform that, right? And you would look at the poles, right? Every pole in the green function and the 2-point function in Fourier space corresponds to a particle, right? That is how you would diagnose the particles in your theory. Good. This is a very fundamental principle. Just a thought for you guys. What happens if somebody gives you a 2-point function where there is a pole on imaginary values of K and omega? Do you guys have any thoughts on what that is called? In physics, that's called a resonance. There's a beautiful story of resonances versus stable particles. So when we say particles here, we mean stable particles. Anyway. All right, so we continue our review. So that was the story of the free propagator. Then we said in the perturbation theory that we set up gives you Born series. Born series could be, we basically organize in the following way. There would be an interaction term, and it's sandwiched with 2 free propagators. Now, the picture to have in mind are these cartoons that you have first propagator, their interaction happens somewhere, then you freely propagate. So your particle is like mean free path, right? Your particles freely propagate. Although these are just formal intervals, right? These are formal intervals. This is not to be taken literally. But the picture is this: the particle propagates for some time and some place, and then at some point in space-time, U and T interaction happens, and then it propagates freely. Now, because you don't know where in space-time this interaction happens, you would have to integrate over the location of this interaction everywhere in between your Ti and Tf. Then we said, luckily, because we had picked the retarded propagator, we could just remove the domains of interval and push it to minus infinity and infinity. This is the first order contribution to a propagator. Then, even though the expression, the integrals look ugly and complicated, the principle is easy to generalize once you start drawing these kind of Feynman diagram looking things. So basically the nth order in perturbation theory, your propagator looks like free propagation, interaction, free propagation, interaction, so on and so forth. And you're integrating over the positions and times where these interactions can occur, right? So any questions about this part? So this is the summary of the first part of what we went over last lecture. This is baby version of Feynman diagrams. Well, they are Feynman diagrams, but
just a quick check. If we flipped the plus I epsilon to minus I epsilon, still taking the limit where epsilon's coming from positive down to 0, that's the advanced propagator, right?
You would have to. No. So no, you would have to. You want to pick up the contribution of the pole, which means that you want to circle around it, right? You would have to go around the circle. So, yes, correct.
Yeah, that it just like flips the two.
You would have to close the contour from below. Yes.
Yeah.
Okay.
You
switch the direction where you close the contour. Yes, correct. Sorry. Okay. Any other questions? All right. then in the previous lecture, we defined the S matrix towards the end. We said that we are assuming that the interaction at far infinity in time, past and far future turns off in an adiabatic way. This is an assumption. Sometimes it could make it rigorous, sometimes it cannot, but let's just assume that for now. If that is true, then in the language of canonical quantization, long time ago, your theory was a free theory. So you could canonically quantize it, you get a Fock space. We call that Fock space the in-Fock space. So there's a vacuum of the in-Fock space. There are excitations, creation, annihilation operators that will create in particles. All of this is occurring at the Hilbert space at minus infinity in time. Now you do the similar thing at plus infinity in time. You get a Fock space that at plus infinity, there's like vacuum out, there are the creation annihilation operators that create annihilate out operators, right? Now, the one particle S matrix is when you pick some one particle wave function of the in Hilbert space, you take a one particle function of the out Hilbert space, and in between, you put time evolution, but of the interacting theory. Good. So, and then you take the limit of TF and TI going to minus infinity plus infinity. That is the object that's called S matrix. So let's just pause and think about this for a second. It's important that the definition of S matrix clicks. So you start with what we call asymptotic states. Asymptotic states exist at minus infinity in time and plus infinity in time, under the assumption that we have turned off the Hamiltonian adiabatically, the interaction adiabatically. So you have an in Hilbert space. The relation between in and out Hilbert space, these are just Hilbert spaces, right? So time evolution of your interacting theory, it starts with this one particle thing, evolves it forward and reaches plus infinity, and then you compare it with your out, what you'd call an out particle. There is an important principle here. The principle is that what you call a particle, right, could change in quantum field theory. We've said this principle before, right? Here we are seeing a manifestation of that happening in time. What looked like a particle to you at minus infinity in time, same excitation as you evolve in time might not call it a particle in plus infinity. In particular, if you have particle creation, that will not look like that, right? If you don't have particle, well, anyway, I'll not go on a rant. Okay. So, all right, so that is the S matrix. Now the perturbation theory that we set up for the propagator actually could be used to get a perturbative expansion for the S matrix. The S matrix that to the zeroth order comes from the fact that there's a term in the Hamiltonian, which is just free theory. So the free theory, if you just plug it in, you're going to get momentum and energy conservation. Because then the in and out Hilbert space are just related by simple phases. Every excitation is evolving in time, every A and A dagger. So if you recall, A of t was e to the power of I omega t A of 0 in canonical quantization. So that's all that there is in the free case. The interaction case would look like this. So this is the K1, right, with the appropriate integrals. And you would have to sandwich it with initial and out, in and out states. And I don't know if you guys are familiar with tensor network diagrams, but I like this picture. So this part is that K1 that we saw before. This means just integrated against an in Hilbert space wave function. This means integrated against an out wave function. Good. If you have never seen tensor diagrams, ignore this. Good. So this is the perturbation theory that we set up for the scattering matrix, S matrix, in this Born series in quantum mechanics. Good. This is the summary of what we went through in the past lecture. Now, today, we're going to generalize that and talk about quantum field theory. But there are two things that I want to tell you guys before moving on to quantum field theory. So I want the connection to quantum field theory to be step by step. So, all right, so now let's just talk a little bit about this. When we did quantize using path integrals, what the object that I was obsessing about was the propagator. And then I said propagator is an observable because it's an amplitude, right? Something is prepared and something comes out. And then you look at the amplitude squared is a probability for a particular transition. What about other observables in the theory? I said that if I said observable, I talked about the matrix elements of observables. And then I said that path integrals, in a very nice way, give you matrix elements of time order observables. But in these matrix elements I was talking about, one vector was always some in vector, right? Some initial vector, and final vector was always some final vector. You might ask me, how do I get vacuum correlation functions? Right? So this is what I'm just going to go through is a very deep insight in path integrals. And it's all about, actually, it underlies a lot of important key results in quantum field theory that relate the S matrix to correlation functions. So now I'm asking, if I'm only interested in the expectation value of the following time-ordered operator in the vacuum, I don't want to know about matrix elements of this in between some initial state I prepared and some final state. I just want to know what is the vacuum expectation value of this observable. How do I calculate that using path integrals? There's a beautiful trick. Is it clear what we're going to do? Good. You start with this matrix element of the observable of interest, right? So this is QITI, this is QFTF. And now this had a very nice path integral expression. Now insert resolutions of identity in the middle here and here, right? Focus on this term and focus on this term. This is S something, this is an orthonormal set of states in the Hilbert space. S Q of F e to the power minus ITFH in the Schrodinger picture. And this is similar. Now, if I, just for simplicity, imagine Ti and Tf are minus T and T. I'm just making it symmetric. And then I'm adding a complex imaginary part to time. I just want to do this by hand, right? What I'm going to do is I'm going to change my Tf to this, and then Ti to that. It's a trick. It's a complex trick. Now, if I look at this object and take the limit of T going to infinity of this, well, let's expand this. In the energy eigenbasis, this looks like sum over n energy eigenstates, En, right? Now, e to minus I T-En, this was the part that I had that was oscillating. And because I added a piece that was imaginary, I epsilon, I get e to minus epsilon T-En, right? Now, if I take the T going to infinity limit, this term suppresses all states that have non-zero energies. So energy is positive. The vacuum is, let's say, is a unique state with zero energy. So this limit projects you to the vacuum. The core idea is the following thing. Limit of e to minus epsilon h epsilon going to epsilon th, sorry, t going to infinity is the projection to the vacuum. This is the key idea. Is that part clear? You should really, this is an important bit. This is also intimately tied to this I epsilon prescription I was talking about, but let's not jump around, right? So this is a projection to the vacuum, okay? So what do I get? I get the following expression for this term. For this term, I get projections to the vacuum. For this term, I get projections to the vacuum. And what comes out of it looks like when I take this limit, of t going to infinity with, I'm no longer writing the I epsilon shift in time. With the I epsilon shift in time, I get a vacuum expectation value of this time order correlator multiplied by these phases. These are some phases that are actually properties of the vacuum wave function, right?
Here, hello, I have a question.
Yeah,
So here, the vacuum refers to the ground state.
correct.
Yeah,
So
for some lattice model, the we think the ground state is still have some energy. So
yeah, so
yeah,
you're asking me what do you do when you have negative energy, right?
yeah.
The important principle in physics is that energy is bounded below, right? And when energy is bounded below, you can always shift the lowest energy state to zero to make sure all energies are positive. As a matter of fact, we did this before, right? Well, if you recall, when we calculate the energy of scalar field in quantum field theory, we saw that the energy was divergent because we had an infinite number of momentum modes, and each of them was contributing half h4 omega. And I just said, what matters is the notion of a lowest energy state. The absolute value of it doesn't matter. I can arbitrarily shift it and redefine energy such that that ground state has zero energy, right? So it's the same principle here.
Okay. So I think there is some difference between the vacuum of Heisenberg picture and the vacuum of interaction picture. Is this correct?
Okay. Yes, that comes up in perturbation theory. Yeah. Yes, that exists. What I'm saying right now here is fully non-perturbative. So at the moment, what I'm doing is just formal, in a sense, formal manipulations. My Hamiltonian might be completely crazy and still using this funky shift. Where is it? Using this, using this funky shift, I can project to the vacuum, right? So this trick is fully non-perturbative in general, but depending on the setups you talk about, if you're in perturbation theory, you might talk about vacuum of the free theory, vacuum of the interacting theory. So that's a little bit more complicated. Here, what I'm talking about is the vacuum of the interacting theory.
Okay, thank you.
Because it's the Hamiltonian of the interacting theory. As a matter of fact, this is just like any positive operator you put in here, this projects to the vacuum subspace of it. That's just what it does. Now, there are these annoying factors here. How do we get rid of them? Well, it's pretty easy. You just divide this path integral by the path integral that doesn't have any operating exertions. Then this term that in the denominator, the analog of this term in the denominator is omega omega, which is 1. So what you get is these two terms, they are independent, they just cancel, right? So what you end up with is this beautiful formula that relates the vacuum time order correlators and path integrals. You always need this normalization. This normalization is not negotiable. Good. So to summarize, we used some sort of a funky analytic continuation, sending t to t minus I epsilon to connect these transition amplitudes to vacuum correlation functions. And this relies on the fact that Hamiltonian is a positive operator. So e to minus epsilon h, epsilon ht in the limit of t going to infinity projects to the vacuum. This I'm always allowed to do. This is a fully rigorous method. Good. Any questions? So by now I've argued that path integrals give you pretty much everything. They give you matrix elements of observables, they give you time order observables, they give you vacuum expectation values, they give you S matrices, they give you everything, all the observables of the theory. So it's a an equivalent formulation of the quantum theory. Good. We'll see that actually there is a way to go in the opposite direction. There is a way, there will be an LSC formula that will relate, we'll learn about this later, that will relate the correlation functions to the S matrix. So these are all related using analytic properties, but we'll get there. But so for now, it's clear, right? I'm just saying path integrals could be used using this analytic continuation to give you vacuum expectation values. Good. All right. Before we move on to QFT scalar fields, I want to also mention one more thing. I think it's a good moment to say this. This path integral we've been working with. Sorry, let me back up. So this path integral we've been working with, we formulate this as a formulation of quantum mechanics. Now, what I'm going to tell you is that even in classical physics, path integrals appear. They actually appear naturally in finite temperature classical physics. And the way to relate the two, that's called statistical field theory, is through what's called weak rotation that sends time, real time, to minus I tau. So let's just work that out a little bit. Here was your propagator, real-time propagator. So it's this in the Schrodinger picture, right? If you say that t is minus I tau, you end up with e to minus I tau f minus tau I. Let's set tau I equals 0 and tau f equal to beta h bar, all right? What you end up with is this. This looks like matrix elements up to normalization of the thermal density matrix, right? So the thermal density matrix is related to the propagator under the following analytic continuation, weak rotation, right? Now, if you take this matrix element and integrate over all Q, that's calculating the trace of the partition function for you, the trace of e to minus beta h, otherwise known as the partition function, z of beta, right? So what we learn immediately is that because the propagator had a path integral formulation, the partition function has a path integral formulation. So now this integral over d of q, so this is a path integral over all dq of tau, e to minus 1 over h bar, 0 to beta tau. These were my ti and tau I and tau f. This new action is not the same as the old action because my derivative has changed sign. T going to minus I tau will give an extra minus sign in front of the kinetic term, right? Now, this integral over Q is implemented. I can implement it by requiring periodic boundary conditions, which is Q of tau is equal to Q of beta h bar plus tau. Now, all right, so what did we do? We started with this phase, Feynman phase. This was a phase that was giving you a weight for every path in the path integral. We changed this to an actual honest to goodness weight, something that could be turned into probability measure. And the log of it is what we call Euclidean action. If it's real and positive definite, it gives a very well-defined path integral. So I know that I'm going through these quickly, but I want you guys to have seen it because it's very deep in physics, this connection. Using path integrals, you could calculate the vacuum. So you could calculate the partition function. If you calculate the log of it, the log of the partition function has a name. It's called free energy, right? 1 over beta of that will give you the vacuum energy. You're using path integrals in classical field theory. This is a deep connection between classical and quantum. is called classical quantum correspondence. On the classical side, what is important to keep in mind is that you're in finite temperature, you are in d+1 spatial dimensions. In the quantum side, you have a quantum system in d spatial dimensions. So you have traded in vacuum, you have traded one extra dimension. The root of this connection is here. The origin of this is the connection between the heat equation and the Schrodinger equation. If you take the Schrodinger equation and send t to I tau, it looks like heat equation. And that beta h bar that I introduced is because I wanted this to look like that. So this is a very deep connection between the two. And so that if you want to have a picture in mind is this: in finite temperature, you have thermal fluctuations, right? Because you're at finite temperature, the system exchanges energy with the bath. There's a probability for such an exchange. In quantum mechanics, you have vacuum fluctuations. You're not exchanging energy with anyone. This is vacuum fluctuations. The probability for exchange in classical physics at finite temperature was always positive. It's a probability. Here, it's an amplitude. It's an amplitude for vacuum fluctuations, hence the I. That's why e to the power of is Lorentzian quantum field theory is a phase, right? It's an amplitude, whereas in the classical physics example, it's just a probability distribution. So in this correspondence, classical finite temperature fluctuations become quantum fluctuations. Good? That's as far as I'm going to go. If at the end of part 1 of the course where we're discussing classical field theory, I was doing finite temperature field theory. I could have introduced path integrals there exactly. I could have introduced renormalization, and I could have totally taught quantum field theory just using finite temperature classical physics. That thing is called statistical field theory. It's a legitimate subfield of physics. It's a very, very big field of physics. One way, for those of you guys who are interested, one way of formally define quantum field theory is through the connection with classical physics. This is a route that you take by analytic continuation of the so-called Whitening function. So you first define the field theory in the Euclidean side, and then you analytically continue. All right, anyway, so I'll stop here. Okay, so what did we do? We said that the path integrals can give us correlation functions if you do this analytic continuation. We also commented on the fact that the path integral can be interpreted as preparing for us matrix elements of density matrix, finite temperature density matrix of a classical system. Any questions about that? All right. So now we're going to switch gears. We have reached the end of our discussion of classical, quantum mechanics. Now we're going to go to quantum field theory. So we're going to do path integrals for free scalar field theory for today. Not tomorrow. Next lecture, we're going to start setting up the perturbation theory. But first, we're going to do free field theory, free scalar fields. In the transition from 0+1 to 1+1, quantum mechanics to QFT, your Q hat operators becomes a field operator. I've added some variable A there. Keep in mind, you could have some sort of many fields, right? Your PI becomes pi A. This is the canonical conjugate variable. All right, so what changes in the path integral? In the path integral, the propagator was, in quantum mechanics, was QF, TF, QI, TI. Here, you have a propagator in between two functions, right? This function is at some later time. This function is at some earlier time. So your path integrating here you have fixed phi minus, here you have fixed phi plus. This is space-time, right? Tnx. And you're path integrating over all functions that have this guy as a boundary condition and this guy as a boundary condition. Right? Okay. So, but as I said earlier, so this picture looks like I'm doing it in real space. But when you do this properly, you first get a path integral in the phase space. So you have a path integral over field phi, and you have a path integral over the conjugate field pi. This is the exponent. This is all, yeah, okay. Now, if the Hamiltonian is quadratic in pi, then we can perform the path integral over pi to get a functional integral only over phi. This is the analogous, this is analogous to the quantum mechanics statement of getting a path integral over real space. Good? Is this part clear conceptually? So that's what we were doing in doing path integrals in field theory. That's what it means. Any questions? This notation just refers to the boundary conditions we set. All right, so now I want to calculate this path integral. I want to do it explicitly. Let me do the following. First, let me use an integration by parts to write down the action for Klein-Gordon free scalar field in the following way. That's just a one-liner. Hopefully it's clear. I can write down the action this way. I'm already going to shift this by minus I epsilon because the task, if I shift this by minus I epsilon, it shifts my Hamiltonian by minus 1 I over 2, and it will help me calculate correlation functions, as I just earlier described, right? So here's what I'm going to do. Now, very good. So this is my partition. This is my action. I'm going to calculate the so-called generating functional. This is the analog of partition functional in statistical physics, classical physics, right? Fine temperature. What is this? You introduce a variable j. This is a source that you couple to your field phi in the following form, linearly, and then you put your action up here. This is called well, this is a partition function. This is the generating functional, right? Is this familiar at all? Have you guys seen the generating functionals? It's a common trick in physics. Well, you'll have a homework problem about this in case it's unfamiliar. It's a common thing that we use with Gaussians. Anything that's Gaussian, we use the generating functionals for it. It's the characteristic equation. Yeah, anyway. All right, so now let's take free scalar field, which means plug in this S0 that I had here up here. So I have to do the following path integral. I'm going to call this Z0 of J, 0 referring to the free field theory. Are there any questions about the form of this integral? I'm writing it as d of x, but this is dd plus 1, right? So these are all, I'm suppressing all sorts of things here. Is this good? All right. Now you recognize this as being related to the Feynman propagator. So the Feynman propagator is a Green's function for this guy, right? Here is a super quick trick. This is perhaps one of the most beautiful tricks in path integrals. You shift phi of x this way. It's a change of variables that will turn this term into a complete square. In the new variables, you will have in path integral over d phi prime, e to minus is naught of phi prime, and pops out e to the power of minus half, jx, jy, the propagator. this is something that is this clear? It's just really a change of variables. You could do this very quickly and see it. It's sort of like a one-liner. So just take phi of x and write it as phi prime plus this term. There is delta of f appearing all over the place, but then when this guy acts on it, this differential operator acts on it, what comes out of it is just the Dirac delta function, so it could perform the integrals. This is the core idea of Green's functions, right? That's why they're nice. So you find that the path integral with the source z0 of j is the path integral without the source multiplied by this thing, because this part of it is just a free sourceless path integral. Does anyone, is it clear why this change of variables works? So in the path integral, field is a dummy variable. The same way that x in an integral is a dummy variable. So field redefinitions are just, it's an arbitrariness in the integral, path integral, right? What you're calling field phi, I can shift it by something and call it something else. I can even like take some nonlinear transformation of the field and give it a different name. From the point of view of the path integral, it won't matter. This is a very important concept in the renormalization group. But yeah. All right, so what we found is that z0 of j is z0 of 0 multiplied by this explicit form. In fact, in your homework, you were going to work out this z0 of 0 and find it to be the determinant, to be related to the determinant of this differential operator. This has to do with, and the determinant of a differential operator needs to be regulated in infinite space, blah, blah, blah. This is stuff that you're going to learn about in your homework. Now, if you want the correlation functions, here's how you do it. You recall the way I calculated the correlation function was by taking z0 of j. I'm doing that like t going to t minus I epsilon. I'm not writing explicitly, right? So actually, yeah. Yeah, good. So this is just a direct application of the principle we saw earlier, right? How to write down expectation value time ordered operator in terms of path integrals with this little trick where you send t to give some sort of imaginary part to the time. Good? Okay. Now, if I have this and start differentiating with respect to j, what do I get? I get correlation functions, right? So this is that's why this is the generating function for correlation functions. The endpoint function, the time ordered, but it's a generator for the time ordered correlation function. This is the beauty of path integrals. They naturally time order things. Want it or not, what pops out is time ordered. So the time ordered endpoint function, this guy, vacuum endpoint function, is this generating functional. You take n derivatives of j with respect to j, and then set j equals 0 at the end. This is just how you calculate it. Right? So now I can write this in a package this in a nice way as the nth derivative of log of z naught of j. This is how you calculate the endpoint functions. Any questions? So this was my log of z naught of j. It was log of z0 of j, which I don't care about because it does the derivative, this derivative will kill it, right? It's independent of, it's just a constant, right? It's independent of j. Minus half j Feynman propagator j. All right, so let's take derivatives of this expression. It's very easy. You first take the first derivative, you get this expression. You'll have to set j equals 0, you get 0. So the 1-point functions are 0. You want to take two derivatives, you take two derivatives. First, term will knock off both of the j's. The other term will give you the following multiplication. These are the rules of functional derivatives, functional differentiation that we went over earlier many lectures ago. You get on top of this, the Feynman propagator, 2 extra terms, but when you set j equals 0, they both die. So you learn that the time-ordered 2-point function and the vacuum is the Feynman propagator up to I. Good. In free field theory, just taking these derivatives, you can convince yourself every time you take an odd point function, the final result will be killed once you set j equals 0. So all the odd point functions, correlation functions vanish. All the even point functions, there's a very simple rule to calculate it that I'm going to explain in a second. But just this, because it's a Gaussian, every time you take an odd number of derivatives, the odd point functions of a Gaussian probability distribution always vanishes. It's just a very simple statement, right? If you have something like this, right? E to minus x squared. And if your x is like this, the expectation value of this will vanish because the probability is symmetric, but your function is asymmetric. Whereas this holds for all the odd point functions, and even point functions will pick up. Will be non-zero. Questions? So now, just some notation. This was the expression that we found that we use as our generating function, log of the generating function, log of the generating function. I'm going to denote this in the following way. I'm going to use the same notation I was using before. These j sources, I'm going to put crosses, purple crosses, and write j under them. And then this Feynman propagator, previously I was just free propagator, I was just drawing a line and calling it K0. Here is delta F, right? So here's what it is. This is the Feynman form for it. This is a single particle propagator because we're dealing with a multi-particle theory. This is a single particle propagator. And there are 2 sources. This is the same old picture that we were drawing in our perturbation theory. Now, in this picture, in this pictorial way of representing things, Z0j over Z0 is e to minus half this guy. So if you expand it, you're going to get 1 minus half this guy plus 1/8 this guy squared plus blah, blah, blah. So you start calculating correlators. The 4-point function, you're going to get these terms. These are things you're going to work out in your homework. But basically, the picture is this. There are four sources. There are 3 ways to contract all of them. There's this way, there's this way, there's this way. All 3 of them contribute equally. The generalization to higher point function is also very simple. Because you have to pair them, that's why all the odd point functions vanish. When you have an even point function, you have to sum over all pairings, not taking the order into account, right? That's just the principle. And these diagrams, these diagrammatic way of drawing things will give you the answer. This is free field theory. These are the endpoint functions of free field theory. Any questions? All right. Now, these were statements about correlation functions. There is a bit more important statement. It's called Wick's theorem. Wick's theorem is a rule for operators. So it's a rule for reducing the time-ordered operators in full geometry. It's an operator statement. So time-ordered time-ordered of two operator insertion, this is an operator, is equal to the normal ordered expression plus the vacuum 2-point function. Now, just sanity check will tell you that if you calculate this, take this operator equation and put it inside the vacuum correlation function, vacuum expectation values, the this guy, the vacuum expectation value is 0. Do you guys remember why? By definition, in normal ordering, all the annihilation operators are to the right. So they act on the vacuum and they'll kill the vacuum. Good. Now, there are all sorts of statements of this type that follow from this. The time ordered, this is an operative statement. Time ordered e to minus I dx jx by x is the normal ordered one multiplied by e to minus half the Feynman propagator. These are very, very convenient rules. If you ever get your hands dirty with these calculations, which you will in your homework, you're going to learn that these expressions are super handy. And then finally, I want to comment on this 4-point function as another example. So the 4-point function, the time order thing, will be the normal ordered one plus the normal ordered 2-point function with 2-point function expectation value plus all the permutations, and the 2-point functions plus the permutations. So again, sanity check, if you insert this inside a vacuum, the first line and the second line vanish. The third line is all that remains, and that matches this picture. Good. Any questions? So this is free field. What we're doing is that we're performing the path integral for free fields, free scalar field. And we found this Gaussian structure. We found Feynman propagator is the 2-point function and time order 2-point function. And we saw that path integrals give you this super convenient way of producing correlation functions. All the odd point functions vanish. All the even point functions are calculated using Wick contractions. Because you know the generating functional is just a Gaussian, e to minus half integral of j propagator j. Keep this guy in mind. This is your friend. This guy is your friend for free field theory. Okay, any questions? So in the remaining time, I also want to comment on the mass gap. I said this earlier when we were calculating the 2-point function in canonical quantization, and when we looked at the 2-point function separated in space, we saw that in massive free scalar fields, it falls off exponentially fast, like e to minus m. And then I said m is like inverse correlation length. That was based on the quantum classical correspondence that I'm going to make precise now. So 1 over m is to be interpreted as correlation length. This is going to be correlation length in fine temperature classical physics. So here's your propagator, right? We wrote it as an integral over d plus 1 dimensions of this Fourier propagator in the Fourier space of this form. I'm going to do the Wick rotation. Under the Wick rotation, the Feynman propagator goes to the Euclidean 2-point functions. Now, if you just follow this change of variable, you're going to get 1 over p squared plus m squared down here. There is a very useful trick that you will use in quantum field theory all over the place. It's writing 1 over a as half integral from 0 to infinity of minus a t over 2. It's a trick that we use all the time. And you can easily see that taking derivatives of this, this just turns into a million different relations. For log of a, it turns into a relation for 1 over a to the power of n. It's something that is commonly used in complex analysis, but anyway. So using this, I take this expression and write it as as dt to 0 to infinity of e to minus p squared plus m squared t over 2. Inside, the rest is the rest. I just copied it. There's some algebra to do, but you first change the order of these two integrals. Then you complete the square in the exponent, go to spherical coordinates in momentum space because this is a d+1 dimensional interval. After you do these 3 steps that you will do in the homework, you'll find that the thermal 2-point function will take the following form, which might look ugly at first, but it's actually kind of, it's super intuitive. There are these gamma functions. These are just constants that depend on dimension. Don't worry about this part. An integral 0 over time from 0 to infinity of e to minus m squared t over 2, e to minus x squared over 2. By the way, there is a lecture by Feynman. I should probably dig this, where he goes through interpreting every single of these terms in like very physical sense. It's a beautiful lecture, but I don't have it off the top of my head. But anyway, and then the remaining is an integral over dp p to power of d e to minus t p squared over 2. Oh, there might be a type. No, this is d. That's good. Yeah, it's not d+1. Good. You do integrals. You go through. I've done them step by step for you to make sure that you could follow. At the end, this is the expression you end up with: half 2 pi x over m to the power of minus 1 plus d over 2, a Bessel function. What is this? Let's recall. This is the Euclidean 2-point function. It's a 2-point function of the finite temperature classical field theory that we found by analytically continuing t to I minus I tau. This is the same Bessel function that you find in your homework when you calculate the 2-point function of the QFT. I don't know if you've done it yet. So there's a homework problem that you'll derive this. Now, Bessel functions, you could expand them in small and large arguments. If you do that, that gives you the short distance and long distance behavior of the 2-point function. In the short distance, it behaves like 1 over distance to the power of d minus 1. In the long distance, it behaves this way, and it decays like e to minus m distance. This is the very meaning of correlation length. You're now in finite temperature. You're looking at the 2-point Euclidean function. And the exponent up here is 1 over m is called correlation length. That's the very definition of correlation length. So mass is the correlation length. Does anyone have any understanding of why this is x to the power of d minus 1? What is in the short distance limit? What does the theory look like? In the short distance limit, there's a term that you can ignore in the Hamiltonian. What is it?
The first one, the about t, right?
Mass term.
Oh yeah.
And in the short distance limit, mass term could be ignored. Your theory is massless free fields. This power is fixed by dimension counting. That theory is scale invariant. The 2-point functions of that are fixed by scaling arguments, just dimension counting, dimensional analysis. The 2-point function of that is fixed by dimensional analysis. I can do it on the fly for you if you guys want. So it's phi del mu phi. This whole thing has to have dimension d+1, sorry. We're in d+1 space-time dimension. So what is the dimension of phi? The dimension of phi is d minus 1 over 2. Because these are derivatives, they are worth 1, dimension 1. Which means that if you have a 2-point function of phi, what should it be? It should be 1 over x to the power of d minus 1. Just dimension counting. Dimensional analysis fixes this for you. Maybe this was quick, but you can work it out for yourself and see that it's true. This principle is actually, there's a deep connection between correlation length, how in our modern understanding of quantum field theory, we view quantum field theory as a deformation of a conformal field theory. These deformations are these mass terms that we're deforming. Anyway, One more piece of terminology that I want to say is called a mass gap. You might hear this a lot in physics. A mass gap is when you're Hamiltonian, you take your Hamiltonian and you look at a spectrum. We said that we normalize the spectrum of the Hamiltonian so that the vacuum has energy 0. In physics, we often want the vacuum to be unique, except for if you take part 2 of this course, it will be spontaneous symmetry breaking. We'll talk about the manifold of vacuum, or topological theories. That's another example. But in all these theories of interest that we're talking about, the vacuum is unique. The first energy eigenstate, if this is non-zero, is called a mass gap. Here, the theory what we're dealing with will have a mass gap and it's m, meaning that the only way to have any excitation on top of vacuum is to spend at least energy that's m. You need at least energy amount m to create something. Can someone give me an example of a theory without mass gap? What is a theory that you know that's not like that? Out of all the examples we've gone through.
No mass gap. Superfluid.
There's
Superconducting.
a simpler theory. Yeah, that's true, but there's a simpler theory. Photons. Photons are massless modes, so you can give it as much energy as you want because the energy is decided by the momentum, right? So the frequency, sorry, the energy is decided by the frequency. So QED is a theory without a mass gap. That will give us a lot of trouble. A lot of trouble. Theories with mass gap are easy because correlations decay exponentially and they're under control. Theories with massless modes are complicated. Another example of theories without mass gap are called CFDs, conformal field theories. They don't have mass gaps either. But anyway, so in summary, path integrals give correlation functions. We argued for that using this trick. We said that Wick rotation connects classical physics, finite temperature physics, to quantum physics, exchanging thermal fluctuations for quantum fluctuations. The same way that for those of you guys who know about phase transitions, the same way that classical phase transitions have to do with singularities of the partition function. Here, you might find quantum phase transitions at 0 temperature, because in this classical quantum correspondence, you go from finite temperature to 0. Those are called quantum phase transitions. Anyway, I'm perhaps talking too much now. All right. Finally, we quantized free scalar field using path integrals, and we found correlation functions using Wick's theorem. This was a summary of this lecture. Are there any questions?
You mentioned that there's a correspondence between like finite temperature classical and like zero temperature quantum.
Yeah.
But isn't there a field called like finite temperature quantum field theory also?
Say it again.
Isn't there a field called finite temperature quantum field theory?
Yes.
And so how does that correlate? What is that correlation of that with the classical case? Is there any?
There is a relation. You basically have yet another dimension. So yeah, that's okay. Let me not get the quantum finite temperature case is more complicated for reasons that I can describe. But the formalism, you know everything. Okay, here let me just say it. So if you have a 1 + 1 dimensional quantum field theory, what is the path integral that you would have to do? You would have to do a path integral in 1 + 1 dimensional space-time to get the vacuum. The path integral you would have to do to get this theory at finite temperature is a path integral. So this was in R1, 1. You would have to do a path integral in R2 cylinder. To get what? To get the partition function, sorry. To get the partition function. Z of j. Z of beta, sorry. But what we're interested in is usually a little bit, so what there is the informalism, there's like a long story for finite temperature. But if you want to just like have a way to think about it, this is basically a partition. This is something you get by putting the theory in Euclidean space and wrapping it around.
Okay.
What happens is that there will be both quantum and finite temperature fluctuations. Both of them are present. Okay, any other questions? No? Okay, if there are no, actually, given that we have like a few minutes, let me just do a very quick count. I don't know how, can I do a poll here? How do you do, oh, poll, no, yeah, poll. Here we go, create a poll. How many of you guys are going to take UFT2? How do I do this? Poll, how many are you going to take UFT2? Choice 1, yes. Choice 2, no. I guess, no, I'm not gonna give you guys, I don't know. Sorry. What happened? Did I post something or? No, I did not, right?
I can't say anything at least.
Okay, sorry, I messed up. Are you taking QFT2? Whoops, yes. No. How do I post this? Do you see it now? What did I do?
No.
Interesting. All right, why don't you just like how do we just
Maybe like we can raise our hands for the people who want to take it.
1 second, let me see. I think I can figure this out. I can figure this out, hopefully, if this thing works. Well, yeah, can you raise a hand? I don't know. This is. Oh, I launched
yeah.
it. Oh, okay.
Yeah,
But
got it.
now I have 2 of them. So answer the first one. There are 2 of them. I don't know why.
I only got the notification for a single poll.
Oh, okay.
So I don't know.
And I guess it would be helpful for me because how I end what I include at the end of this semester will crucially depend on how many of you guys are gonna take QFT2. I guess maybe I should have asked how many of you guys are leaning towards formal theory as well, but theory versus not theory. But anyway, it doesn't matter. If you ever have any suggestions or something, just ask. Are you done? Should I end the poll? I don't really see the answers. The technology is sometimes too complicated. Are we good? Yeah? All right. I'll end the poll. Share results. I don't even see results. How do I share them when I don't see them? Okay, it didn't work. Sorry. Never mind. Can you just I'll post it on Slack. All right, good. Any questions, guys? I should probably stop the recording for sure.